Hello, this video is to help you with the key to the homework 6. We have 6 questions here, and we're going to start from the first one until the last one. First, let's take a look at the first one, the 9.5.4. So this is about the hypothesis about the proportion. Okay, so the first part right here is about the point estimate, right? Because here we are interested about the proportion and how to estimate the proportion, right? This basically is the point estimate. Point estimate, think about this one. 117 out of 484. So that's a proportion, right? And then specify the null and the alternative. The null, because think about other data engineering horizon consistent with the claim. What is the claim? The claim, 1/2 of all engineers continued academic study beyond the BS degree. Okay, so that's we come up with the hypothesis P equals 0.5, and then are the data of engineering horizon consistent with the claim, right? Consistent. If it's consistent, that means P equals 0.5. If it's not, that means it's not equal to 0.5. The only thing I want to mention here, what is the P0? P naught actually is this guy. This is the P naught, okay? All right. For part 4, what is your conclusion? Because we could have 2 ways here. First way is the so-called critical value method. For the two-sided alternative, we have 2 critical values, right? Positive and negative for the z-test right here. Oh, here should be positive, negative 1.96, okay? And what is your conclusion by the p-value method? P-value method, this is the definition for the p-value because this is a two-sided test. Yes, this is almost 0, okay? Of course, we reject the null hypothesis on both methods. Why? Because for the p-value, because this p-value is almost 0, alpha equals 0.05, of course, we're going to reject the null hypothesis. For the critical value method, why we also reject the null hypothesis? Because think about the critical region, right? Or rejection region. There's a bell-shaped right here, and then 0, and then we have what? 1.96 and negative 1.96. These are 2 critical values, and the critical region either less than negative 1.96 or greater than positive 1.96 on 2 tails, okay? And we know our observed value actually is what? Is this guy, right? Negative 11.36, which is on the left end, right here. You can see is in the rejection region. That's why we reject the null hypothesis. And also, this is a good chance to talk about the p-value, because our observed value is right here, right? Negative 11.36. So our p-value is either less than this guy or greater than this guy, okay? Two-tailed. Don't forget it's very easy to get the next side, left side, excuse me. But don't forget there is a positive side also. Here we just say P 2 times P, the probability of capital Z greater than positive 11.13, because these two are what? Asymmetric, right? This one is the Z greater than 11.36. This one is Z less than negative 11.36. All right, and then the third way to do the hypothesis test is the confidence interval, and use this formula to get a confidence interval. And we know 0.5 is here should be 0.5, excuse me, okay? 0.5, is it in it? Actually, it's not, right? Because 0.5, think about 0.5 is greater than the upper end, right? So it's not in it. Since it's not in it, we're going to reject the null hypothesis. That's the rule for confidence interval. And for part 7, for beta, we just follow the formula from the notes, right, for the beta. The only thing I want to say here, because this is for two-sided test, right here. Yes, is not equal to 0.05. Then the z should be 1.96. Why? Because alpha is 0.05. Z should be alpha over 2. Okay, so yes, we have to use this one a lot of times, all right? That's the only thing I want to say, because don't mess up this. Alpha has to be split by 2 because it's two-sided test. All right, and for part 8, do you think engineering horizon would commit a type 2 error? Why? This one, we need to understand the whole logic of hypothesis, right? Think about what is our conclusion. Our conclusion is reject the null hypothesis. Reject null hypothesis, there's only chance to commit what? Type 1 error. Because you got to know what the definition of these two types of errors, right? Type 1 error and type 2 error. You got to know the definition. So here, since we reject null hypothesis, then there's no way they can complete type 2 error. And for this one, we need to know what's the definition of z beta. Z beta actually is defined as, if you check the notes, you'll understand is what? This is the z beta. And then the probability for capital Z greater than little z beta equals beta, okay? This probability equals beta. So for the beta 0.1, so z beta is about 1.282. Okay, this is from the R. So plug in and then you round it up. All right. Now let's take a look at the second question, 9.72. So this is about, the section 7 of chapter 9 is about so-called goodness of fit. Remember in our notes, the example is also about the Poisson distribution, right? But that Poisson distribution, there is no mean. Okay, here we just say, okay, lambda equals 1.2. Is that correct? And there is no lambda. Then you have to estimate the lambda, right? Remember in the notes, we have to estimate the lambda. What does it mean? So if here 1.2 is not given, then you have to estimate. About how to estimate, please refer to the notes, okay? Yes, based on the observations, we're going to estimate the lambda head. Here we don't need to because we already specified as 1.2. All right, for the goodness of fit test, what is the parameter of interest? Actually, the parameter of interest is what? Is not really a parameter, is a what? Is a form of the distribution for this random variable capital X. And then we say the formal distribution is a Poisson. Actually, you can see it a little bit more with lambda equals 1.2. Or you can say, yes, this formal distribution is not a Poisson. All right, what is the observed value of the test statistic chi-square 0? Construct a table like we did for example. Yes, this is exactly what we're talking about in the notes. So with the value 0 from 0 to 3, and then the last one actually 4 here, we cannot just say is 4, is what? 4 or more. Why? Because we know the Poisson distribution is what? Could be any possible number until to the infinity. Okay, there is no end for Poisson distribution. So how do we get this probability? Because here I can only do one because of time, right? Because you see here we got to go probability of x equals 10, uh, equals 0, okay? Yes, this is x values. And then by the Poisson formula, we have e to the power negative 1.2 lambda, then 1.2 to the power k, here is 0, and then divided by 0 factorial. Okay, so this is about this big. All right, if you have questions about this, please refer to the notes we did in class. Okay, after we get the pi, then expected confidence frequency is going to be n times pi. What is n? N is, you just add all this together, all the frequencies together, right? In this case, we have 100 observations. So here is 100. And then use 100 times each of those individual probabilities. The only reason I want to say the last one, because after you calculate each of those four probabilities, right? The last one is going to be 1 minus the sum of these four. You got to guarantee you add all those four probabilities together, the sum should be very close to 1. Okay. All right. After we finish this table, then we have the observed frequency and we have the expected frequency. Then just follow the formula for the chi-square statistic, right? OI minus EI. OI is the observed frequency. EI is the what? Uh, expected frequency, and then square it and divide it by the expected frequency. So we calculate this number is about this big, okay? What is the p-value? For the p-value, here we have to specify what is little k and what is little p. Little k means how many categories you're gonna come up with, okay, for the values. Here we have from 0 to 3, and then 4 or more, we have 5. That's why we have k equals 5. What is p? P, if you check the notes, you know this p means how many population parameters to specify this distribution. So here we have the Poisson distribution. We know Poisson distribution only has one population parameter. So that's why p equals 1. Then df equals little k minus little p. And then minus 1. That's why we got 3. Okay. All right. How to get it? That's why the p-value is defined as this way. Because for the chi-square, the p-value from the table unknown, we could not find the probability exactly, but we could just get the range, okay, p-value from the chi-square table. Why is that? Because think about it as, for 3 degrees of freedom, this chi-square is like this kind of shape, okay? So this is chi-square distribution with degree of freedom of 3. And we observed as what? As this big, right? 7.0. Let's just round it as 03. So what is the p-value? P-value is right here, right? That's the p-value. If you go to the chi-square table, you won't get exactly p-value, right? Because this cutoff point is not one of those specified in the table. But we do know for the alpha equals 0.05, the cutoff point is what? 8.72 is about here, okay? Let's just say it's right here. 7.82, excuse me. So, and we know, even though we do not know the p-value is exactly, but we know this p-value actually is going to be bigger than 0.05. Why? Because for 0.05 right here, it has a cutoff point as 7.82. Our set of cutoff point observed value is what? Is less than that. That means the error is bigger. Does that make sense? So we could, yes, we do not know what this value exactly, but we do know this p-value is going to be bigger than 0.05. That's going to be enough for us to what? Because the rejection rule tells us whenever the p-value is greater than 0.05, the alpha value, then we fail to reject the null hypothesis, right? That's what I mean by p-value range from the chi-square table. Of course, you could just use the R code to get exactly p-value. In this case, you can see this is exactly p-value from the R code. Yeah, use this one in R, okay? This is the code. And critical value, you can get this number directly from the chi-square table. All right, what is the conclusion? Of course, either by the critical value or the p-value, we fail to reject the null hypothesis. And also, we could just let the R do the whole thing. Okay, those are the code. In the main steps here, you can see your observed count, right? And I specified the reason behind the code. Yes, because of time, I could not explain in detail, but you're more than welcome to try it in your own R. You can see the expected probabilities. These are calculated, and then we calculated the total count, expected count, right? Think about it. So this is exactly the n. Okay, and then we sum together. This exactly calculate the chi-square statistic. And then because our df, remember, is defined as what? Little k minus little p and then minus 1, right? Okay, that's how we got it. 5 minus 1 minus 1 equals 3. And then p-value, you can see, use the R code to get a p-value and then print the result. Okay, so I give you this code because in the real project, right, we do not need to calculate it by hand. This is, to be honest, some of you emailed me saying the calculation is tedious. That's correct. So later in your project, you have a big data set. There's no way you can just do it by hand. Okay, I would not recommend it, but you can use R code to do it. But here, as a course, I really want to push you to do it some by hand. Okay, please do it both. Okay. All right. Now let's take a look at the question 9.83. Okay, this is about these are very informative. This is about section 9.8. So it's about the independence of these two criteria of the same variable. Okay. So basically it says those numbers are what? Are the observed number of the breakdowns for the machines. But these breakdowns could be categorized by two ways, right? Either by the shift 1, 2, 3, or by the full machines A, B, C, D. Now we want to know whether these two types of criteria are they associated with each other? What does that mean? We want to know whether does this shift, right, will cause different numbers of breakdowns. So please understand the logic behind instead of just follow the math blindly. So here, what is the parameter of interest? Specify the non-alternative hypothesis. Here, really, we do not have parameter of interest, right? Interest actually is also, you can say, the distribution of the breakdowns among the shift, right? But more precisely is here, these two hypotheses. Breakdowns are independent of shift, or breakdowns are not independent of shift. Then, based on this table, we could specify the observed and so yes, we could make a table, right? We put a total here, row total, and also we put a total here as a column total. That's how we have those T's, row 1, row 2, right? Because here is 89, 65, row 3 is 58, and the grand total is what? And the column total, we have 87, we have 48, we have 37, we have 40, okay? And then we add all of them together, get a grand total here, okay? And how we're gonna get the expected value? Because those numbers are only what? Observed. For the EIJ equals what? The row total I and column total J. Okay. And then divided by this guy is N. Okay. So yes, because of the time, I do not give that much detail, but please make sure how you can get this, okay? I know this is tedious, but it's worth practicing. You know, you got to practice to understand what's going on here, okay? The table like what we did, for example, 9.14 in the class, in the notes, all right? All right, after we get a chi-square, yes, this is exactly what we get here, all right? See, so the N is that, and then how do we get that? This one. So 36.52 equals what? Because this is the first row, 89, that's the row total. The first column, the column total is 87, and then divided by 212. So, and then the same thing for the others, okay? All right, after you have the observed and then expected, and then follow the formula, right? Like here. Right here, the formula, O minus E squared divided by E, and then add them together. What is the p-value? So p-value here, we need to know, okay, first of all, the degrees of freedom equals row minus 1, column minus 1. So number of rows minus 1 times number of columns minus 1. So in our case, we have 3 rows, we have 4 columns. That's why we get 6 as degrees of freedom. And then this is the observed statistic value. So that's the p-value. Okay, we still have 2 ways as we explained just now, right? Either from the R, you get the exact value, or from the chi-square table, you get what? A range. Either way, we'll end up with what? With fail to reject null hypothesis. You know, our p-value actually is greater than 0.05. And you can see here also from the critical value, because our observed value, chi-square statistic, is only 11.65, but the critical value has to be at least 12.59. So this one is less than that. So we still fail to reject. All right, this last part I really want to say something, okay? Because you can see this is a lot of calculation, okay? You know, it's not easy to get this table, by the way. And also, you know, calculated the chi-square statistics is also a lot of work. That's why some people complain it's tedious. To be honest, I agree with that. Okay, in the real life, in the project, right, if we have a big table, what should we do? Then we could just use our code to do it. You know, we could just, you know, first of all, we import this observed frequency table into the R. We use this matrix, okay? and then we specify the rows, how many columns, and then we say these numbers can be arranged by row. Okay, that means the first four numbers is the first row, second four numbers are what? Second row, and then third row. All right, and then we specify the names for rows and columns, right? Shift equals 1, 2, 3, machines equals A, B, C, D. And then for the test, you do it in R, it's very easy. Just use chi-square and then put your data table in it. Then it will give us everything. You see, this is the chi-square, this is degrees of freedom, the p-value. See how nice this one is. And then we can even get the expected value for the frequencies, expected frequency values, right? You just say, yes, the chi-square test, and then use a dollar sign, and then you say expected. Okay. And then sometimes you can even say, okay, I use chi-square this test, right? SQ test, and then data. This you gotta specify. You can use a dollar sign and then put a data. It will show us the whole table. Okay. So this is a nice R code. I strongly recommend you master it. It's gonna help you a lot in your career.